One really cool application of hydrostatic pressure, well, more so even the fact that the pressure at any level in a continuous fluid is the same at the same depth. Let's take a look at this particular case. I have some container that has a big opening and a small opening, and I put a piston. Sorry, I didn't mean to draw a wavy line. I put a piston on each opening. Okay. All right, let's say I push down on this with some force. Okay, push down on that one with some force. My question is, how much stuff could I lift? What size of a box could I lift over here? Or in other words, what upward force would I get? So let me do F in and F out to emphasize. What outward force would I get? Well, we know that at any depth, so the pressure here is the same as pressure here is the same as pressure here, but also the pressure here is the same as the pressure here because they're at the same depth. And so if I push on this left side, the smaller side, then with the pressure being the same, I can calculate what that pressure is, remembering that force equals pressure times area. So I would have F in equals pressure times A in, and then F out would equal pressure times A out. And so I can try and compare those. I could say I could divide these two equations, and I get F in over F out equals A in over A out. Or rewriting it, I can get F out equals F in A out over A in. Okay? And so if I double the area on the output side compared to or if the output area is double that of the input area, I can get double the force output. So I can push with 1 Newton of force, and I could lift something with 2 newtons of force because of the virtue of the pressure in the fluid. Now this might sound, okay, that's neat, but in true applications, we could make this side over here teeny tiny, maybe a millimeter in cross section, or millimeter circle in cross section, and we can have the output be a meter in cross section. Now there is 1,000 times 1,000 or a million square millimeters in a square meter. So that means we could get an output force of 1,000,000 times bigger than the input force. You can buy at a hardware store a bottle jack, which is basically this principle that can be like a 20-ton, 25-ton bottle jack, where you squeeze down on a lever and presses on a small little piston, like this one on the left side. And on the output side, it's the size is such that you can put up 15 tons worth of you can lift 15 tons worth of stuff. And I've used them myself on lifting up beams of houses to hold entire ceilings and roofs up. You can use it to hold an entire house up. It's really amazing with just the press of a lever we can do that. A car jack is probably most familiar example, and it's again impressive with being able to apply a small pressure with your hand can lift an entire car off the ground. So this is a really cool application. So the main idea is that the areas and the forces are proportional.